Open an app on your phone, tap a single button, and within 3 seconds, a car is assigned to pick you up. It feels like magic. But underneath that simple screen, there are millions of riders and millions of drivers all over the world, and every single one of them is moving in real time. If a computer tried to measure the exact inch-by-inch distance between your phone and every single moving car in your city at exactly the same time, the math would instantly overload and crash a standard server. It's simply too much changing data to process at once. To solve this massive physics and computing puzzle without crashing, the system has to rethink how it looks at the map. To track cars, the system divides the city into a grid. Each square gets a unique code, and drivers constantly update their location. When you request a ride, it ignores 99% of the city, searching only your box and its neighbors. Engineers call this method geohashing. By chopping the globe into these tiny, manageable pieces, finding a driver shifts from an impossible global math equation to a very fast process of asking, who is inside this specific box right now? Once that search area is locked in, the system starts looking at the available drivers currently sitting inside your specific grid square. It figures out how long it will take each car to reach you. It does this by measuring the physical distance on the map and then adds in the current live traffic delays for those specific local streets. The system then takes the drivers with the best arrival times and sends a ride offer to their phones. The first driver to tap accept wins the fare and heads your way. This digital request flashes from the main servers directly to the driver's phone in a fraction of a second. Because the grid completely narrowed down the number of cars the computer had to look at, the system bought itself enough processing time to handle all those complex traffic calculations instantly. But there is still one major hurdle. On a busy Friday night, you aren't the only person asking for a ride. Millions of people are pressing the request button at the exact same time. This diagram shows a load balancer. Think of it as a traffic cop catching a massive wave of incoming ride requests at a central point. Instead of letting one computer get crushed, it instantly deals requests out evenly across dozens of individual computers. Without this traffic cop keeping the flow perfectly smooth, the grid math wouldn't be able to start. The front door of the entire system would simply jam shut. So when you open your phone and hit request, your signal flies to the load balancer, which catches it and hands it safely to a computer with enough room to work. That computer immediately looks at your specific square on the invisible grid to find the cars driving right near you, ignoring the rest of the city entirely. It runs the local traffic math, pings the best options, and secures your driver. And it does all of this heavy lifting in about 3 seconds. Every time you press that button, the system repeats this process millions of times across that digital grid to get a car to your door. Next time, we'll look at the system design behind the streaming giant Netflix and how it manages to push video across the globe without buffering. Follow along to master system design step by step.